In this lesson, we will focus on Task 3.3 from Project 3, which involves the comprehensive diagnosis of machining quality issues and process optimization in the integrated planning of milling, planing, and grinding for typical parts. In the metal cutting process, machining quality is crucial as it directly affects the performance and the service life of the parts. We will explore how to accurately diagnose machining quality issues and improve machining quality through process optimization. This will be accompanied by real-world case studies to help you better understand and master this knowledge. In metal cutting processes, milling, planing, and grinding are common machining methods used to manufacture various typical parts. However, machining quality issues inevitably arise during the process, necessitating comprehensive diagnosis and process optimization. First, let's understand the relevant concepts of machining quality. Machining quality primarily includes two aspects: machining accuracy and surface quality. Machining accuracy refers to the degree to which the actual geometric parameters, dimensions, shape, and position of a machined part conform to the ideal geometric parameters. The closer the actual values are to the ideal values, the higher the machining accuracy. Machining accuracy can be further divided into dimensional accuracy, shape accuracy, and positional accuracy. Dimensional accuracy refers to the degree to which the actual dimensions of a machined part conform to its ideal dimensions, typically controlled by dimensional tolerances. For example, if we are machining a shaft with a diameter of 50 plus or minus 0.05 mm, 50 mm is the ideal dimension, and plus or minus 0.05 mm is the dimensional tolerance range. Shape accuracy refers to the degree to which the actual shape of a machined part's surface conforms to its ideal shape, such as cylindricity and flatness. Positional accuracy refers to the degree to which the actual position of a machined part conforms to its ideal position, including parameters like parallelism and perpendicularity. Surface quality refers to the microscopic geometric shape errors of the surface layer and the physical and mechanical properties of the surface layer after machining. Surface quality has a significant impact on the wear resistance, corrosion resistance, and fatigue strength of the parts. The indicators of surface quality mainly include surface roughness, surface waviness, and changes in the physical and mechanical properties of the surface layer. Surface roughness refers to the small spacing and minor unevenness of the machined surface, typically measured by parameters such as the arithmetic average deviation of the profile, RA. Next, let's discuss the comprehensive diagnostic methods for machining quality issues. When machining quality problems arise, we can analyze them from multiple perspectives. From the perspective of the machine tool, the accuracy and performance of the machine tool directly affect machining quality. The geometric accuracy of the machine tool, such as the straightness of the guideways and the rotational accuracy of the spindle, impacts the shape and the positional accuracy of the parts. For instance, if there are errors in the machine tool's guideways, it may result in out-of-tolerance flatness when milling a plane. The transmission accuracy of the machine tool, such as the transmission accuracy of the screw nut assembly, affects the dimensional accuracy of the parts. We can ensure the accuracy of the machine tool by regularly conducting precision inspections and maintenance. The cutting tool is also a crucial factor affecting machining quality. The geometric shape of the tool, the sharpness of the cutting edge, and the wear condition all impact the machining quality. Tool wear can lead to increased cutting forces and higher cutting temperatures, thereby affecting machining accuracy and surface quality. For example, after tool wear, the roughness of the machined surface may increase. We can ensure machining quality by observing the wear condition of the tool and replacing it in a timely manner, or by employing tool wear monitoring technology. The properties of the workpiece material also affect machining quality. Different workpiece materials have varying mechanical and machining properties. For instance, materials with higher hardness tend to cause tool wear during machining, while materials with better toughness are prone to forming built-up edges, which can affect surface quality. We need to select appropriate machining processes and tools based on the characteristics of the workpiece material. The selection of cutting parameters is also crucial. Cutting parameters include cutting speed Vc, feed rate F, and depth of cut AP. Excessive cutting speed can lead to increased tool wear and higher cutting temperatures. An overly large feed rate can increase surface roughness, and an excessive depth of cut may cause vibrations, affecting machining accuracy. We need to reasonably select cutting parameters based on the workpiece material, tool material, and machining requirements. For example, during rough machining, a larger depth of cut and feed rate can be selected to improve machining efficiency. During finish machining, a smaller feed rate and appropriate cutting speed should be chosen to ensure machining accuracy and surface quality. Let's further illustrate the comprehensive diagnosis of machining quality issues and process optimization through a practical case. Suppose there is a part with a milled plane, and after machining, it is found that the flatness is out of tolerance and the surface roughness does not meet the requirements. We first inspect the machine tool and discover that there is some wear on the machine tool's guideways, causing slight tilting of the work table during movement, which is one reason affecting the flatness. Next, we check the cutting tool and find that the cutting edge is worn and there is built-up edge adhesion, which affects surface quality. Then, we examine the cutting parameters and find that the feed rate is too high. To address these issues, we carry out process optimization. For the wear problem of the machine tool's guideways, we perform the maintenance and adjustments on the machine tool to restore the precision of the guideways. Regarding the tool issue, we replaced the tool with a new one and used an appropriate cutting fluid to reduce the formation of built-up edges. For the cutting parameters, we appropriately reduced the feed rate and adjusted the cutting speed to ensure machining quality. After process optimization, the part was machined again, and both the flatness and the surface roughness met the requirements. When conducting process optimization, we must adhere to international guidelines. Internationally, there is a series of standards and regulations regarding metal cutting processes. These standards and regulations have been developed through long-term practice and research, and they possess scientific validity and authority. When planning processes, we should refer to these international guidelines to ensure that our machining processes comply with international standards. At the same time, we must coordinate all aspects, including machine tool operators, tool designers, and process planners, to work together to create optimal value. For example, machine tool operators must strictly follow operating procedures. Tool designers need to design appropriate tools based on machining requirements, and process planners should develop reasonable machining processes. Only through the coordinated cooperation of all these aspects can we improve machining quality, reduce costs, and create optimal value. In this lesson, we will focus on the comprehensive process planning of milling, planing, and grinding for typical parts in Project 3, specifically Task 3.3, which involves the comprehensive diagnosis of machining quality issues and process optimization. We have learned that machining quality includes machining accuracy and surface quality. Machining accuracy encompasses dimensional accuracy, shape accuracy, and positional accuracy, while surface quality includes indicators such as surface roughness. We have mastered the comprehensive diagnosis methods for machining quality issues, analyzing from aspects such as machine tools, cutting tools, workpiece materials, and cutting parameters. Through practical cases, we have learned how to optimize processes to address machining quality issues. Additionally, we emphasize the importance of adhering to international guidelines in process planning and coordinating all aspects to create optimal value. I hope that, through this lesson, everyone will be able to accurately diagnose machining quality issues and effectively optimize processes in actual metal cutting operations.